Well, hello, everyone, and welcome to the Ida B. Wells High School Astronomy Club. I think this might be our last meeting of the year, the 2021-2022 school year, and I'm very excited to introduce our guest, a high school student finishing up her junior year at Joseph High School, who has done a project that she would like to share with you. Her name is Molly Curry, and Molly, you have permission to share the screen, so I'm going to hand it over to you right now.
All right, thanks, Joe. Hi, everyone. My name is Molly, like Joe said, and I did a project this year using spectroscopy to study stars. So I'm going to give a little bit of background information before I get into what my project actually was. One thing that's important to know is that color and temperature are the same thing. And contrary to the popular belief that blue equals cold and red equals hot, in reality is the opposite. And we see that in stars. So the hotter the star, the bluer the light is that it emits. And the colder the star, the redder the light that it emits. Another thing that's important to mention is brightness and luminosity are the same thing as well. Brightness is used more commonly in astronomy, and luminosity is used in astrophysics because it's an actual physical measurement of how much energy is being radiated by a star, and it's measured in watts. Brightness and absolute magnitude are also interchangeable, and absolute magnitude is how bright an object would be if it were placed exactly 10 parsecs or 32.6 light years away from Earth. That's not to be confused with apparent magnitude, which is how bright stars appear from Earth, because distance has a factor in that. For example, Sirius, the brightest star in the sky, has an apparent magnitude of negative 1.46 and an absolute magnitude of 1.42, while our sun has an apparent magnitude of negative 26.74, but an absolute magnitude of 4.83. Annie Jump Cannon made instrumental discoveries in astronomy and was also did groundbreaking work for women, especially women getting educations. She studied physics and astronomy at Wellesley College, which is in Massachusetts. After taking a break from astronomy, she became a teacher there. She taught junior physics. At the same time, she took graduate classes and enrolled in Radcliffe College, which was the women's part of Harvard, because at the time Harvard was completely male. She published her first star catalog of over 1,000 stars in 1901. She also worked on the Henry Draper catalog at Harvard College Observatory as a computer, which was a group of women that were hired and very, very underpaid to compute and look at spectra and classify them. She also developed the Harvard spectral system, which I'll go into more detail about later. It's a classification of stars based on their temperature. She was appointed as the curator of observational photographs at Harvard's observatory. And during her lifetime, she classified over 350,000 stars. Some sites I looked at actually said 500,000. So that's a lot of stars to look at and classify. And like I said, she made great steps forward for women in education. She was the first woman to get a Doctor of Astronomy degree from Groningen University, the first woman to get an honorary degree from Oxford, and she was also the first woman to be awarded the Henry Draper Medal of Honor. Later in her life, in 1938, she was appointed as a Harvard faculty member, and she retired in 1940, but worked at the observatory until her death in 1941. The Harvard spectral system started in the 1880s when Wilhelmina Flemings decided to classify stars by the strength of their hydrogen absorption lines. And she originally classified them A through O, A being the strongest absorption lines and the weakest as O. And in the 1890s, Annie Jump Cannon revised that classification. And instead of starting over, she took 7 of the classes and rearranged them by temperature. And so this is what she got. The 7 main groups that stars are classified into: O, B, A, F, G, K, and M, from hottest to coolest, M being the coolest. So our sun is a G2b, which means that it's kind of in the middle of those classes. The 2 means that it's a relatively bright G star. So stars are also given a number from 0 to 9, 0 being brighter than 9. And the V just means that it is a main sequence star. If you look in the top right corner where my mouse is, there's a list of other additions to that, like a supergiant would be an LA or LB, and then bright giants are Roman numeral 2. If you look along the bottom here, you can see all of the classes, and you can see that they're organized by temperature, O stars being above 30,000 kelvins and M stars being from 2,400 to 3,700 kelvins. And also the light that they emit is here. In the 1910s, I think, 2 astronomers were working independently. Danish astronomer Ejnar Hertzsprung, pictured on the left, and Henry Norris Russell is pictured on the right. They were working independently and each discovered a really interesting pattern when they graphed stars by their temperature and their brightness. And their discoveries proved that there is an organizational principle in the properties of stars that before had seemed kind of random, and their work also helped to explain the stellar life cycle. So this is what they found, the Hertzsprung-Russell diagram. On the bottom, the x-axis, you have temperature and also spectral class, and temperature and color are also the same thing. So blue and the hotter temperatures on the left, and then cooler temperatures in red on the right. On the y-axis is absolute magnitude or brightness and luminosity, which are the same thing. So you can see that there's the main sequence, which is where most stars fall after they're born and before they die during their life cycle. This graph does a better job on the right of depicting the color and the classes where different stars fall, where their main sequences and white dwarfs and giants and supergiants. So my project was using spectroscopy to study stars. So what is spectroscopy? It splits light into individual wavelengths. You can think of it like a rainbow, except instead of only 7 colors, there are infinite wavelengths. So you can see that you can use a prism or a diffraction grating. Prism is demonstrated in this picture down here, and the diffraction grating is in the right corner. And so how we can study stars using their spectra is because each element has a spectral fingerprint. You can see in the bottom corner, these are some spectra of elements, hydrogen's on the top and helium, and you can see some of their emission lines that are bright right there. And so we study stars using spectra because you can see that they're made up of different temperatures based on which absorption lines they have, because each element creates absorption lines at a certain temperature. So for my project, I took spectrograms of 6 different stars, one from every spectral class, using Sean Curry's telescope. He has a home observatory in Medford, Oregon, and I was actually able to control it from my computer, which was really cool. And we used one star from about the middle of every class because we wanted to look at roughly the middle of every class to compare each spectral class. And so you can see the HD number for every star. That's just the Henry Draper catalog, which was published with about 225,000 stars from 1918 to 1924. So the procedure for my project, first, Sean and I met to plan our observation night, which ended up being pretty difficult because there was only one clear night that we could actually observe. So the second meeting, we gathered the data using his telescope and spectroscope. We met a third time to process the spectra, and a fourth time to analyze what we were looking at. This is a clip from AstroPlanner, which is a software we used to plan our observation night. It looks kind of confusing, but I'm going to just point out a few key details. So over here, we have the name of the stars, which has its Hipparchus number or its Henry Draper number. over here, and we use the HD numbers. You can see the spectral type, which we had to sort through because we wanted only stars, not variable stars or double stars to take spectra of. The altitude was also important to look at because we needed it to be above the horizon, which meant over 35 degrees. We had to make sure that it was rising, it had risen and would not set before we were observing. And we also had to make sure the magnitude was above 7 because his telescope couldn't pick up anything dimmer than that. And then the last thing we had to do was sort through the spectrum. So there are a bunch of stars here, but only some of them are main sequence stars or 5 stars. So we had to sort through all of these and make sure to find the ones that we wanted to observe. This is the equipment that we used. This is his telescope, which we didn't actually look through it. I was at my house and he was in his office controlling the telescope virtually. So this is the spectroscope right on the bottom right, and this is it attached to the telescope. It's right there. And this is what it looks like inside. So what happens inside the spectroscope is the light enters through this slit right here, and we had to move the telescope to align the star with that opening, and then it enters through here, bounces off this mirror, and goes through the grating, which separates the light into the individual wavelengths. And then it bounces off of this mirror. And finally, it goes to the sensor where it takes a picture over duration of time. And this is what we got. So this is an unprocessed picture of our A5b star, which it doesn't really look like much. Like we can't really tell. You can see some black lines, which are the absorption lines, but we can't really tell what this means. But interestingly enough, this is what Annie Jump Cannon looked at to classify stars. She didn't have computers. They didn't have the technology that we have then. So she could look at this with like a microscope, not a microscope, but one of those glass things, and tell you which kind of star this was, which is pretty impressive. But we have computers now. So when we look at spectra, it looks like this. This is that same star processed. So you can see the wavelength along the bottom from 4,000 to 7,000 is within the visible spectrum. And Sean's telescope can actually see into the ultraviolet over on the left and into the infrared. And on the y-axis, we have relative intensity. So this is showing how much light it is emitting at these wavelengths. This is a stacked chart of our results, every star. The O star is on the top, and it goes down in brightness, so the M star is on the bottom. I wasn't actually able to take the spectra of the M star myself because it wasn't up, and M stars aren't easily visible with his telescope. So we actually used data that Sean had already gathered last year, I believe, of Bernard star. But the other 6 we took together, and they're in order. So you can see that the O star is actually peaking very early on in the graph, which means it's emitting more light at a shorter wavelength, which means that it is a hotter star. And Bernard star is peaking over farther on the right at longer wavelengths, which means that it is a cooler and redder star. So let's talk a little bit about absorption lines. Photons, stars emit photons, and the elements in the atmosphere absorb them to change energy levels. Certain elements absorb photons at certain temperatures. So what we're looking at here, you can actually tell the temperature of the star based on which absorption lines appear, because those elements are absorbing photons at certain temperatures. So for example, hydrogen, the optimum temperature at which it will produce the darkest or deepest absorption lines is around 10,000 kelvins. So hydrogen lines actually don't appear in very hot stars or very dim stars. So here you can see a bunch of absorption lines. The red lines are ones that I noted while after processing the images. The H, zeta, gamma, beta, and alpha, those are all hydrogen lines. This one right here is a sodium line. This is a carbon line. That's helium. This one is a calcium line. And this one, I can't read it, but I believe it's helium, if I remember correctly. So we know that our results are very accurate because we did an instrument response correction in Demetra during the processing step using a standard star spectra that was taken by professionals. And our wavelength calibration accuracy was 0.4 angstroms, which angstroms are very small. So that means that our margin of error was very little. And this over here on the right is just a picture that I found of spectra of stars, which looks relatively like ours. So we know that our results were pretty accurate. If I were to do this project again, I would really want to do it in person. I didn't get to set up the telescope or the spectroscope or even look at any of the equipment very closely. So I think it would be really cool to do another project in the future where I'm actually doing some hands-on work. And also I would have really liked to gather my own data of an M star. There are a bunch of more complicated steps that we could have taken or more projects that we could add on to this that we could have done. One is look at spectra of more stars inside of the spectral classes, such as looking at a star from every class inside of the A class, like an A0V through an A9V, to compare what their spectra look like within that class. Another really advanced step that we could have taken was converting the spectra from relative intensity to absolute flux, which is measured in ergs per centimeter squared per angstrom per second, which would show us the intensity, how much light the stars are actually emitting comparatively to each other, because the y-axis was kind of arbitrary during my project because we didn't take the step to see how bright this star would be compared to this star. So that would be really cool to see, but we didn't have time to do that. Another thing we could do would be to take spectrograms of unusual stars like Wolf-Rayet stars, which are very, very hot, massive stars that have burned through all their hydrogen and they've started to fuse helium or even heavier elements at their core. One of those stars is actually pictured on the top right up here. That's a Wolf-Rayet star surrounded by a nebula that the Hubble telescope took. And they have very, very high surface temperatures to burn helium or heavier elements, from 20,000 kelvins to 210,000. For reference, our sun burns at about 5,800 kelvins. So when you look at their spectra, they show emission lines, which instead of absorption lines go down. Emission lines should show up as spikes in the graph, and they show up as ionized helium and nitrogen or carbon. And I think that would be really cool to look at. We could also change the line grading that we used. So we used a 300 line grading, which shows absorption lines of 8 angstroms wide, which is pretty good. But if we had used the 600 line grading, we could have seen absorption lines 4 angstroms wide. And the only downside to that would have been that the spectrum would be smaller. We would have only seen the visible portion of the light instead of being able to see into the ultraviolet and the infrared. Thank you guys for listening. Do you have any questions?
Well, before we take questions, would everyone turn on their, here, I'm going to stop sharing for just a second. We can go back to that.
I have a question right off the bat.
I wanted to clap first, though, Rob. So I tried to
yes.
get everyone to show up here first. So yes, so you in a minute you can turn on your microphone or put questions in the chat. But first of all, that was an excellent presentation, Molly. Thank you very much. Oh, there's everyone. There's everyone. All right. Okay, Rob. You know, Rob, I think many of you know this, but not all of you. Well, exquisite amateur astronomer is a professional optical engineer. So this is the sort of thing that he dedicates his life to professionally and as a hobby. So take it away, Rob.
Thanks for setting me up for this home run shot now, because it's not so much as a question as an offer. I have a spectroscope of my own, one that I in fact made. I use 3D printing. I make my own holograms, and the spectroscope is a combination of grating and prism. This is called a grism. And this spectroscope is not a measuring instrument, but it's a visual instrument. I'm going to bring it with me to Wallowology, and I would like to show you some of these spectra in the eyepiece. They're very beautiful, and in particular, I can show you an M star that is quite bright actually, and also a Wolf-Rayet, and you'll see an emission line. So I'm just making an offer for you to come and see this thing in real life. And if I can tell you're already excited about spectroscopy enough to go do this kind of a project remotely without ever having touched the telescope. And I'm hoping that being able to touch the telescope will just make you even more excited about it. So, and fabulous presentation, really well done. I think that, like Jim Todd said, this group does presentations at the college level and above, and yours is right there. So good work.
Thank you. Yeah, that sounds awesome. That would be cool.
Yes, any other questions from any of the students or comments? I know it's finals week and you're all exhausted. I am too. Molly, is it your finals week or do you have one more week of school?
I don't have finals.
No finals. When's the last day of school?
It's next Tuesday.
Yeah, so you got a few more days than us. Tomorrow's our last day of school and then 3 days of final exams. Brendan, did you have a question?
No.
Oh.
Go ahead.
I didn't have a question. I just wanted to say that was an amazing presentation, and I was incredibly impressed by the level of accuracy that you were able to achieve, especially from not even being there in person. The presentation was great. The research was fantastic, and like you mentioned, there's so many different ways you can go after this project, and you seem like the perfect person to do it. And I'm currently probably going to go out to Wallowology, so maybe I'll meet you there.
Yeah, that'll be cool. Thank you.
Yeah, that's great. And Logan went out to Wallowology last year and met Molly, and hopefully we'll get to go again this year. Rob asked, what's the difference between a carbon star and an M star?
That's me.
I don't think anyone's going to know that except for you, Rob.
I honestly don't know. When I looked at the spectra you took, it looks very familiar. So maybe I'm looking at an M star when I think I'm looking at a carbon star. I don't know, but they have that unique look of very broad spectral lines and obviously very red. So I don't know what the difference is. I really don't. And
I just Googled it real quickly to confirm my impression, but here it is from Wikipedia. A carbon star is typically an asymptotic giant branch star, a luminous red giant whose atmosphere contains more carbon than oxygen.
Okay.
I'm not totally sure I know what that means. Hey, that'll give us something to do next year. Hey, I do want to acknowledge that it is finals week and you all have finals to study for. I did, though, I kind of messed up before. I would like everyone who is willing to turn on your camera or at least your microphone and give Molly a round of applause. We do hope, Rob and I think as everyone here knows, I am retiring from Ida B. Wells High School, but that does not mean I'm retiring from teaching. And it doesn't mean I'm retiring from the Astronomy Club. And at the very absolute least, Rob is going to continue the telescope group. But we hope there will be more activities in the Astronomy Club. And we hope to keep reaching out. So people like Molly, who lives 6 hours away, but who loves astronomy, can participate. And maybe Sean Curry, the mentor for this project, was telling me he knows some kids down in the Rogue Valley, the other corner of Oregon, who want to participate. I don't want to commit myself to too much right now because I'm exhausted like everyone, but we're going to do some more great things. And I think that's our last meeting. I hope you all do have a great, exciting astronomical summer. Some of you I'll see, some of you I won't, but I will check emails. So thanks again, Molly. Thanks everyone again for coming. Thanks as always for coming and helping out Rob. And good night, everyone.
All right, thanks.
Thank you so
And
much.
thanks for the
Yeah.
presentation. That was really
Yeah,
interesting.
Great job.
Yeah, thanks for listening.
Thank you. That was a great presentation.
Thanks.
All right, cheers. Thanks, Joe. Thanks, Molly. Wonderful.
Rob. Molly, stay on for just a second.
Thanks, Rob.
Rob didn't come out to the Wallowas last year, so I don't think you've met him. He's a pretty amazing. He's a pretty amazing man. He's actually more of an engineer than a scientist, although I don't want to underplay his scientific background or knowledge. But he is one of these guys who can build anything, which I am not. And he's quite an amazing, what we call eyepiece astronomer, somebody who can look through the eyepiece and tell you a lot. Which curiously, Sean is not. Sean is a data astronomer. He hardly ever looks for the eyepiece anymore. He analyzes data. There's just so many different ways to enjoy the hobby or to make it an actual profession. That was really good. They are all very polite people, but they weren't just being polite, telling you how good it is. That was a great presentation. And I'm going to tell your parents and Ms. Kendall, Ms. Hayes, there's a Ms. Kendall at the school I teach at now.
Oh,
So I knew something wasn't right. Ms. Hayes. And of course, she'll get an A. You did fabulous all year. And I will probably have more things to say later, but I am really about ready to fall out of my chair dead asleep. It's a
me
crazy.
too. I got like 5 hours of
You are-
sleep last night.
Yeah, I loved what you added too. Your additional things were wonderful. Super good. So go tell your parents how impressed I was, and I'll tell them that in an email. Okay, good night.
Good night. Thank you, Joe.